Hey guys, today's lesson is going to be going over U-joint differentials again. So I want to reiterate a little bit about what we talked about on, I think it was Thursday last week. Yeah, that sounds about right. So a couple things that we're going to want to hit on with our drive shafts. So number one, they are used to transmit rotational force over a distance. And they're also going to allow movement between components. And finally, they are typically going to be hollow tubes with yokes welded on to each end. Just a reminder, this is a U-joint drive shaft like we would typically see on a vehicle. So cardan joints, or commonly known as U-joints, we need to remember that they are not a constant velocity joint. Now generally we're going to use them in sets of two, and that will allow them to be a constant velocity, but one U-joint by itself is definitely not a constant velocity. So the proper timing of our joints is absolutely critical for smooth performance of the driveline. Noise, vibration, and harshness is something that we really worry about in the automotive industry, and we want to make sure that everything is set up properly, or we will get a pretty nasty vibration. So speaking of that vibration, the optimum working angle of a U-joint is going to be somewhere between 1 to 3 degrees. And a U-joint driveline noise is usually going to be described as a noise that is relative to, but increases in speed much faster than ground speed. So again, we're going to reiterate here the different components that we actually have. So if we're looking at this, we have the trunnion, which is this component right here, or the cross. We also are going to have our needle bearings and our cap. So we have needle bearings inside of each U-joint. That's kind of one of the things we got to be careful with when we replace a U-joint. And then we have a yoke on each end. It's important to note on this particular one, this would be the slip joint side, because we have a yoke here and a yoke here. So this is going to flex, and then one side is going to slide into the transmission, and the other side is going to be welded to the drive shaft. So when we talked about our drive shafts on Thursday, we do remember that we have two different angles of rotation on this, okay? So our first one, and we'll go to here because it's a little easier to see, we can tell that this one is moving vertically up and down. And now we have the other joint, and that joint is spinning at an angle, okay? That is what creates the difference in speed, because for every time this thing makes a rotation, half the time it's going to be accelerating, and half the time it's going to be decelerating. Hopefully we remember this from that video. The sharper the angle of this shaft is what is going to dictate how much the speed is going to vary. So if we have a really steep angle, this thing is going to speed up and slow down a lot. And if we are basically straight, it's going to speed up and slow down very little or none at all. Okay? So I want to show you guys a video real quick that's going to show you or talk about how the different angles matter, or how it affects the driveline performance. And I'll say it really quickly right now, but if we notice, this flange here is straight across. Then this flange here is also straight across. We need this flange and this flange to have the same pinion angle. And as long as we have that, that can allow everything to keep in the proper orientation and will allow our driveline to work like a constant velocity. Okay, so let's pause this. And we will go to our email. Oh, got you, by the way. So let's look at our drive shaft angle and phasing video. We'll check this out. I'll be back.
This demonstration unit consists of a constant RPM electric motor and 60-tooth sprockets on the drive shaft, as well as the input and output yokes. When there is no operating angle on the U-joint, the output yoke of the driven member, the U-joint, and the drive shaft all travel together at a constant speed. Watch the tape on these sprockets and listen to the sound the card makes as the drive shaft rotates at the same speed as the output yoke and U-joint. When an operating angle is created at the front end of the drive shaft, the output of the U-joint no longer travels in a perfect circle. Instead, it travels in an ellipse. This forces the drive shaft to speed up and slow down to keep pace with the rotation of the output yoke, creating torsional and inertial vibration. Watch the tape and listen to the card. As the output of the U-joint changes speeds, so does the drive shaft, even though the output yoke itself is maintaining a constant speed. When the operating angles on each end of the drive shaft are not equal, the non-uniform velocity is transferred to the input yoke of the driven member. Making the center lines of the driving and driven members parallel will automatically make the U-joint operating angles equal at each end of the shaft. With equal operating angles, the non-uniform velocity of the front yoke is canceled by the non-uniform velocity of the rear yoke. This causes the output of the rear U-joint, the rear yoke attached to it, and the driven member to rotate at a constant speed. This is what we want, a constant speed into the driven member. Earlier in the program, we talked about phasing. Drive shafts that are not in phase do not rotate at a constant speed. Even when operating angles are equal, improper phasing can create a non-uniform velocity in the drive shaft and a torsional and inertial vibration. This is why Spicer recommends marking the components of a drive shaft before taking it apart. This will help you reinstall the components to maintain the correct phasing and reduce the chances of driveline vibration.
Okay, so hopefully that makes a little bit of sense to you guys. Let's go back to our PowerPoint here and let's look at this. So if we have a angle on the input that is similar to the output, we will have a constant output if all things are equal. But we need to remember a constant input speed was going to result in a varying output speed, and then a varying input speed is going to result in a constant output speed. But if these are not lined up and they are not parallel with each other, that causes all the problem in the world. Coincidentally, if these two yokes are not indexed properly, which we'll go over tomorrow, that will cause the same thing. So basically what I'm trying to get across is that driveline angles are extremely critical for noise, vibration, and harshness, which is something that customers typically don't want to see. Now I want to go to the last point, and that is talking about 5 and 6. So the optimum working angle of a U-joint is between 1 and 3 degrees. Now why isn't it 0? So the issue is we need to have some movement in these bearings, or these bearings will wear really bad. Basically it takes about 1 degree to get a complete rotation of each one of these little roller bearings in here. And if they do not rotate, the grease does not get distributed. They end up getting flat spots, which causes them to basically squeak and cause a lot of other noises. So that is kind of a big issue. Now, it's not going to happen. Nothing's going to happen if we're over 3 degrees. Basically, the higher we get above that optimum, the more it's going to bind and the more chance we have for failure in a U-joint. And basically, the shorter the lifespan of the joint. So just remember, we can go above 3 degrees, but it's going to cause reduced lifespan in the joint. So we want to try to avoid that as much as possible. So our U-joint noises are generally going to be described as a noise that is relative to, but it increases in speed much faster than ground speed. So it's kind of a unique thing. If you've heard it before, you can probably pick it out from a mile away. So I want you guys to hear this one time so you can kind of understand what's going on. So let's go back to our video and let's watch this. soon as that thing starts to take off, we hear a squeak, and then all of a sudden that squeak starts getting faster rapidly. The reason it speeds up so much faster than ground speed is because it's attached to the pinion shaft of the differential, which most differentials are somewhere around, let's say, 2.75 to 411 to 1 reduction. So we got to understand that drive shaft is going to speed up a lot faster than the ground speed. So we heard that noise start, and then it sped up till the point that we couldn't actually hear it at all anymore. And then as it began to slow back down, we could start to hear it again. That is the characteristic. If you hear that noise, it's pretty much a dead giveaway. You have a U-joint going bad somewhere on the vehicle. So let's listen to it one more time. That should help. Just bonus points to anybody that noticed that the guy's left front tire is low. It's not flat, but it is low. Okay guys, tomorrow we're going to talk about a little bit what goes on with the failures of a U-joint, and we will talk about some driveline angles. I will talk to you later. Bye.